So it's 9 o'clock, so I think we'll get started. So good morning and welcome to all the participants out there. My name is Christy Mortar and I'm the chair of the CTS Infrastructure Research Council. And I work at Hennepin County in the Transportation Operations Department. I will be helping facilitate today's webinar and meeting, which is sponsored by the CTS Transportation Infrastructure Research Council. Just a little bit of background on the councils. The CTS councils provide a forum for transportation professionals and researchers to share information on current transportation issues and trends. They bring together university faculty and staff with practitioners from the public and private sectors to recommend direction and participate in improving the center's research, education, and engagement programs. Katie Kirk will share the link to the council's information in the chat if you're interested in learning more about the councils. Today's webinar features several University of Minnesota researchers on the topic of innovative materials and advanced technologies for a sustainable pavement infrastructure. Our chair, our council vice chair, Beth Ingham, is also here and helping to co-facilitate this webinar. Beth, would you like to introduce yourself now?
Sure, thank you, Christy. As you said, my name is Beth Ingham. I'm with CBS Squared. We have an office in Northeast Minneapolis, and we're an engineering, architecture, and survey firm here in the Twin Cities. And as Christy said, I am the co-chair of the Infrastructure Research Council. Just want to go over a little bit of housekeeping today. If you would like to participate or if you have a question, if you could just use the chat function within the webinar here. You can also raise your hand. So I'll be monitoring that to make sure that we're able to answer any questions you might have. I may hold them to the end unless they're specific to the current topic. And then I'll turn it back over to Christy to talk a little bit about the round robin and getting us kicked off here.
So before we do that, I just would like to share that Gina Boss and Katie Kirk from CTS are on the webinar today, helping support the event. And before we get started, I will turn it over to Gina from the Center of Transportation Studies to recognize our outgoing chair, Mark Maloney.
Well, thank you, Christy, and good morning, everybody. It's great to quote unquote see all of you this morning, and it's my great pleasure to say a special thank you and recognize Mark Maloney, who, as Christy mentioned, has served as the Infrastructure Council chair, and prior to that, vice chair. So for the last 6 years, he's been involved with the leadership of the council. And Mark currently serves as the Public Works Director for the City of Shoreview, and I like to call him the guru of permeable pavement. So Mark has been an A+ champion for research for the CTS and the university for many years, not only serving with the council, but also as a member of the local road research board, and just has really brought that local government perspective to the work of CTS and to the researchers at the university. And it's really important because, as he reminds us, the needs of cities and counties are often different than the needs of the state in terms of infrastructure as well as other issues related to the transportation system. So Mark has been a reminder for all of us in that area. And on behalf of CTS and the university, just really want to give a very heartfelt thank you to Mark for the work that he's done for CTS and for the university over these many years. And he's not going away. We know he's still going to be very involved, but just is kind of ending this time as chair of the council. And Mark, we can't thank you enough, and I know I'm gonna miss that connection that we've had through the council coordinating committee and through the council. So with that, again, thank you so much for your efforts on our behalf, and I'll turn it over to you for a few words.
Well, thank you, Gina. I really appreciate that you've humored me on behalf of local government for all these years. It didn't feel this way when I was younger and just breaking into this market. I sensed that local government didn't really have a seat at the research table, and that really wasn't anyone's fault but local government. I think a lot of the people in my market sector are so busy and they don't necessarily immediately recognize the value of creating relationships with research, community. We were more or less just happy to see what trickled down from MnDOT and the federal level. And I really appreciate that the structure of CTS and the infrastructure councils has accommodated the local government perspective. And I think if you look at the membership of the infrastructure council these days, you'll see that that local perspective is baked in. And I think that really does a service to the people that we serve. The local, as you pointed out, local government is related, but sometimes separate from the federal or the state level of transportation agency. And so I hope that we've been able to bring some relevant research topics, and not just bringing ideas, but also bringing partnership and the willingness to kind of be there and be a part of the research projects themselves, whether it's, as you pointed out, with the local road research board and through technical panels, or just looking over the shoulders of researchers and hoping to help to add some value to the process. So it's been great. I'm just really thankful for all of the work that CTS does in general, but specifically the way that you've steered or allowed some of the research energy to be steered towards local government directly. And I think that's paid off to the citizens of the state. They've seen innovation in transportation research, whether it's pavement or bridges. So I'm just thankful. Unless you know something I don't know, I will be around for a little while, but perhaps in a lower profile manner. So thank you all.
Great. Thanks so much, Mark. And with that, I will turn things back over to Christy and Beth.
Thank you, Gina. So now we'll talk about housekeeping. I just wanted to make sure everyone knew how they could participate in the chat. So go ahead and put your comments there, and I'll keep an eye on those. And today, for today's talk, we will be able to issue professional credits. So if you need a PDH form, just put a message in the chat for all panelists, and we'll get you a form following the event so that you can keep track of those PDHs. With that, I believe we're ready to introduce our speakers and get started. Oh, no, we're not. We just wanted to make sure that you're aware that we do have, CTS does have other councils with meetings and webinars coming up. So we've got a couple really engaging topics. Tuesday, October 26th, which is already next Tuesday, we have a webinar on community engaged transit planning. So that will be a really fun one where they talk about rethinking I-94, and it's going to be hosted by the CTS Transportation Planning and Economy Council. And then the final webinar for this fall is the Pedestrian Crossing Experience in Minnesota, which is coming up the afternoon of November 9th. And this will be presented, two presentations exploring the pedestrian experience, both in urban and rural areas across Minnesota. And that webinar is going to be hosted by the Safety and Traffic Flow Council. So go ahead and check out the website, CTS's website, for more information about those two events, which also offer credits. Oh, November 4th, we have the Transportation Research Conference coming up. It's completely online, but you can also get registered right now since it is coming up here quickly. So we've got a great slate of speakers, and so you can check those out also at CTS's website.
Thank you, Beth. So now I'm just going to introduce the webinar. Today's webinar features presentations on innovative material and advanced technologies for a sustainable pavement structure. It's widely acknowledged that early detection of material damage and timely rehabilitation could lead to a significant reduction in the life cycle cost of asphalt pavements. Our speakers today will highlight University of Minnesota research investigating the capabilities of graphite nanoplatelet or GNP-taconite-modified asphalt materials in damage detection and healing. The presentation will focus in on two research components. The first being the application of the asphalt materials for damage detection using electrical conductivity. And then second, the damage healing capability of the asphalt materials upon microwave heating. So I'm pleased to welcome today's webinar speakers. We've got Jia Liang Lei and Mihai Maristano, who are both professors in the Department of Civil, Environmental, and Geoengineering at the University of Minnesota, and Larry Zanko, a senior research fellow at the University of Minnesota Duluth Natural Resources Research Institute. Thanks for joining us today, and I'll turn it over to you guys for the presentation now.
Thank you, Christy. Let me just share the screen. Okay. All right. Very good morning. Thank you for joining us today. My name is Jialiang Le. It's my great pleasure to present this research joining with my colleague, Professor Maristano, and collaborator, Dr. Zanko from UMD. Today's topic is resulting from our recent project sponsored by LRB and the MinDOT as a knowledge-based project on innovative materials and advanced technologies for a sustainable pavement infrastructure. So we will present different aspects of this project, mainly focusing on a new material we developed recently through this project and advanced technology we use to do damage healing. So first of all, I will hand over to Mihai to present to you the background of the project.
Thank you, Jialiang. Thank you, CTS, for the opportunity. We really appreciate that. And also thank you for the panel members and for all the attendees. I see some familiar names and faces, so that's great. And indeed, the background and motivation is very straightforward. Everybody knows about proactive pavement preservation and rehabilitation versus reactive. This has been a topic that has been discussed for many, many years in the pavement community. And basically, it boils down to the fact that if you can actually manage to keep the pavement in a reasonable condition, starting with the early stages of pavement preservation, then we can eliminate very costly repair that are needed if the pavement is not preserved in time, so to speak. So this is something that I guess these numbers have been around for a long time. And a lot of people are talking about it and about pavement preservation, but in terms of practical applications, although there is a lot of work, it's fair to say not enough has been done. And an efficient detection of damage. So when we talk about early stage, what does that mean? Early detection of damage that is not always possible. That is a critical component, and also repair, a timely repair also is a critical component of cost-effective pavement preservation plan. And you have the well-known graphs that I think a lot of people have seen before, how you can actually, by performing this proactive pavement preservation, can save you a lot of money. Next slide. And our focus was, as we mentioned, on early detection and to find out when we start to see, for example, microcracks occurring and other types of damage. And we show here a number of pictures from various methods that have been used, non-destructive test methods. Of course, we are all familiar with destructive test methods that could be more accurate, but also, as we well know, result maybe in a bunch of round holes in your pavement when we take cores. But I would say for the past 20 years, that has been a lot of work in non-destructive testing. There are more and more technologies available, computational capabilities. We are showing here of some of them. And I have to say and acknowledge that some of the methods shown here, for example, Myra, and in particular the rolling density meter, they came out of research and sponsorship from Minnesota Department of Transportation that has been a champion in promoting some of these non-destructive test methods. Of course, there are other methods, digital image correlation, and the ultrasonic test, actually in various forms that have been used. But I guess, as you will see in this research, in this investigation, we actually were trying to take advantage of some unique properties of the new materials to be able to detect this early damage. Okay, so Zhaliang, if you would like to continue, thank you.
Thank you, Miha. So as Miha said, that over the years, that different ND methods were developed. In this research, we take a different route. We were thinking that whether or not we can use the pavement itself as a material to detect damage. So in the literature, some people call it self-sensing. So the material we have investigated for a while is called GNP-modified asphalt materials, and GNP stands for graphite nanoplatelet. So I just want to give you a brief description of what this material is. So GNP, basically, if you think about it, is like a disc. The disc consists of several layers of carbon atoms, which we call graphene. So the disc really has a thickness about submicrons, and the diameter of the disc is about several microns. So it's really small. And so if we receive the materials, it's like a powder, basically. So starting about 2016 or 2015-ish, the team at the U of M has tried to develop this GNP modified asphalt materials, and we look at different properties of the material, mostly mechanical properties. So on the right-hand side, the top figure shows that the comparison of a GNP modified asphalt materials compared to the conventional asphalt materials in terms of strength at low temperature, which is really important in Minnesota. So we tested basically the strength of the material at the temperature minus 30 degrees C. As you can see, that if we add 3% of a different type of GNP by weight to the binder, you can see the strength can be improved more than 50%. So it's really promising material in terms of enhanced load resistance. On the other hand, we also look at the compactability of the asphalt. So when we make an asphalt pavement, we need to do compaction. So on the lower side, on the picture, you see that if we add a GNP, so the blue curve is that we add 6% GNP by weight, and the black curve is that without adding any GNP. So you can see for given the compaction or gyration number, adding more GNP, it will make the material more compactable. So this really tells us that with adding GNP, the asphalt materials can be compacted with less energy, which is important property that to expedite the construction of pavement. Now, we also observe that during the previous research, we see that the GNP material is also highly microwave and absorbing and also conductive. So if do not add the GNP, you may imagine that the asphalt material, it does not conduct electricity, but after adding GNP, it does. At the same time that if we put a GNP asphalt into the microwave, and this you will see what happens. I hope the video will play here. So you can see now something happened. So what you see that is that we put a small amount of GNP asphalt in the microwave, and through micro energy, actually it can generate a lot of heat. And that really stimulates the idea, see whether we can use that to do damage healing. Okay, so that is a very brief background of the GNP material developed at the U of M. And now I want to hand over to Larry to talk about the other part of the material with the Taconite Concentrate. Larry, please.
Sure, thank you. Yeah, and thanks everybody for being here today. I want to thank Shalong and Mihai for having me along on this project. It's been very interesting. Really, the background and motivation for going, Shalong has just talked about GNP, and so has Mihai. A lot of research a lot of research that we've done over the years. I have to give credit. I know that Dave Hopstock is in the audience today, and also Vern Haig, who are both collaborators on this project. David brought to my attention several years ago how magnetite is an excellent microwave absorber, and we have a lot of magnetite in the taconite ore that's mined here in Minnesota, and a lot of byproducts that are generated that I've talked about over the years about being a very good aggregate material. This property, it's inherently enhanced with magnetite, so it makes it sort of a natural choice to use in a pavement application like this. So this is just a very quick example of what that effect is, comparing limestone, sand, quartz, which is basically transparent to microwave energy, versus the three taconite materials on the right, going from left to right with increasing magnetite content. So you can see just over a period of 30 seconds, the difference between each one. So there is a definite heating enhancement with using taconite materials that contain magnetite in asphalt formulation. So next slide, please. And just taking that a bit further, we received cubes that were made down at the University of Minnesota Twin Cities campus that contained a control binder, taconite concentrate only, and GNP plus taconite concentrate binder. So again, these are some experiments that were done with a 1 kilowatt customized microwave heating device that we use, and then some thermal imaging to give you an idea of what was happening. Again, the control binder in the left-hand column, just binder as is, taconite concentrate only in the middle, and then the two together. And this is something that we saw during this project and other experiments, that there was sort of seemed to be a synergistic relationship between having GNP and the taconite concentrate together in a mix. So that again is more of a reason and the rationale for the project as using these two in combination for enhancing, ultimately rehealing or enhancing the strength, long-term durability of asphalt pavements. So I think that might be it for my part right now. Yep.
Yes, so I want to just summarize what is the objective of this research. So this research really look at the 4 aspects of this new material and try to explore the capability of this new material for 2 things. One is damage detection, one is damage healing, which very much align with the ultimate goal of earlier detection of damage and pavement preservation. So we will talk about damage detection through the measurement of electric conductivity. And then we want to talk about whether or not indeed the GNP-taconite-modified asphalt materials will improve the conductivity. And then we will talk about damage healing capability of this new material through microwave heating. And then we will present some application of this new material for Tack coat. So the first topic I want to talk about is the damage detections using electric conductivity. This part is theoretical modeling. Basically, we are asking ourselves that if we have an electrical conductive material, if there's a crack formed in the material, are we able to quantify the extent of the crack through the measurement of conductivity? So this leads to a mathematical model. So on the right-hand side, you can see that I just put a schematic of a specimen with a crack. The crack length is A. And then we put the 2 electrodes on both sides and we measure as a conductivity. Let's assume the material is conductive. Really that the conductivity of the electricity through the specimen is governed by the electrostatic field. So the governing parameter here is the electric potential phi. And if we differentiate this phi with respect to x and y, you get electric field in x and y direction. And the current density is related to the electric field with this linear equation Ji equal to sigma Ei. Sigma here is the conductivity. And then if you write down the balance of electron, you get this continuity equations. Basically nothing but the current flow in x and y direction should be conserved with respect to the charge density change with the time. So if you solve these equations as listed, you are able to draw the electron flow into the specimen. Now the question is that how the conductivity of the resistivity or conductivity of the specimen change with the crack length A? That's the question we want to ask. Because what we will do is we measure the resistivity at the 2 ends, and then by changing the crack length, you will expect that the resistivity will increase as the crack length increase. But we want to get a quantitative relationship between the change of resistivity of the specimen with respect to the length of the crack. When we look at this set of equation, we find that actually this is very, very similar to a stress analysis we did in civil engineering. So we count the same specimen. Now we do not load the specimen with electric field, but we load with loading. So here we are looking at the anti-plane shear stress. So the top and bottom surface, the top surface, we apply the loading into the screen, into the page. And at the bottom, the loading is applied out of the screen. Okay, so you really have a shear loading. And what we call it a 2D anti-plane shear. Under this particular loading, the displacement field of the specimen is UZ in Z direction, which basically is perpendicular to the screen. And the strain, the shear strain gamma ZX gamma Y ZY is basically can be computed by differentiation of the UZ with respect to X and Y. And we also know that from elasticity, the shear stress is equal to the shear modulus multiplies the shear strain. And we also have equivalent equations given by this, where F is the body force. Now, if we compare the 2D anti-plane shear equation to the electrostatic field, you can see that exactly the same thing. Only difference is the notation are different. So in that sense, you can see that displacement in anti-plane shear is analogous to the electric potential. And equivalent equation is equal to the equation of continuity in charge density. So with that, basically we will say that if we are able to solve the problem on the right, actually we can use a solution of the right-hand side solution, the problem to solve the left-hand side. So now, since the electrostatic field is a mathematical analogous with the mechanical field, so the resistivity of the specimen and the electric loading is nothing but the voltage divided by the current. That is exactly analogous to the compliance of the specimen we look at on the right-hand side, which is a displacement divided by the loading we applied. So that really gives us the key point of the model. That's the electrical resistivity. The electrical resistance is analogous to the elastic compliance under anti-plane shear loading. So the change of the resistivity resistance as a function of the crack length is nothing but the change of the compliance as a function of the crack length. And trained in civil engineering, we know how to calculate the compliance as a function of the crack length. We know that. And that is basically by this equation from linear elastic fractional mechanics. This K function is what we call a stress intensity factor. And this K function is known for different crack geometry. For example, if you have an edge crack, you have a center crack, you have a different K function. But this K function, you can find the K function in a handbook. Okay, so if I know the function K and I measured the change of resistivity, then we are able to determine what is the crack length A. So that is really a key idea that we can quantify the damage extent through the measurement, the measured change of resistance of the whole specimen. So to give you an idea that how the model works, so now let's say we have this edge crack, okay, and if we measure the voltage and the current at the two ends of the specimen, okay, and this is what we did in simulations. Okay, we simulated the electrostatic field in commerce, and you can see that if I change my crack length from the 25% of the depth all the way to 87.5% of the depth, those little arrow you see is really the current density flowing through the specimen. You can see that at the crack tip, you do have a very significant concentration of the current density. And if I, as analogy, if I apply the loading on the specimen, if I plot the stress path, you can see same idea here at the crack tip, you have a very high stress concentration. That again, stress is analogous to the charge density here. On this picture, you see that there's a plot of the change of the resistance versus the crack depth. The black curve is the prediction by this equation, and the gray curve is by simulation. You can see that they're really on top of each other. So it shows that this model it really works very well, provided the material is conductive. So theoretically speaking, that if we have a conductive material, we are able to determine the crack size precisely from the measured change of the resistance. So now that next question is that whether we are able to make a conductive material. So that leads to the second part of the talk, which will be focused on the electrical conductivity of GNP-taconite-modified asphalt materials. So now we want to see that whether or not we add GNP and taconite into the asphalt, we can make it conductive. The GNP material we investigate in this project is basically from Asbury Carbon, is a company in New Jersey. They provide us two types of GNP material. One is called M850, which is a graphite flake. Carbon content is 99.54%. Surface area is 13 meters squared per gram. The other one is 4827. This is what they call a kinetic graphene material. It's a higher carbon content. It goes to 99.66%. Surface area is much larger. We are looking at 250 meter square per gram. The reason that the company provides us with these two materials is because of cost. And the company is aware of the potential application of this large quantity for infrastructure. So it's important to keep the cost low. So as you can see, the cost of these two materials is pretty low. We are looking at $3 to $4 per pound. Okay, just to give you a brief idea, if you purchase a single one carbon nanotube, we are looking at $20 to $50 per gram. So it's much more expensive. Okay, so we try to use a cheap material, but can serve the purpose. As I said, the graphene nanoplatelet, the carbon structure is something like that. Okay, we have a layer of a carbon layer. So you can see that this the blue dot is the carbon atoms. Okay, and they formed by sigma bond. And basically we put all these layers, several layers together to form a disk. That forms what we call a platelet structure. And on the right-hand side, you see this is the material we received from the company. It doesn't look like powder, but if you look into each grain, it's basically a disc-shaped material. Okay, so I want to hand to Larry to talk about the concentrate that we use.
Want to go back to that slide? There we go. Thanks. Yeah, that, as Zhelong just said, looking at materials that are relatively, affordable, as opposed to, okay, carbon nanotubes that they're really, really expensive. The other component that we're looking at is taconite concentrate, which is really the magnetite that's extracted from the ore during processing up on the Wasabi Iron Range, and also in Michigan for that matter. Basically, what you end up with is this is a typical particle size distribution of a couple of the operations that generate this material. You can see that for the most part, it's 100% passing a 100 microns, and then a significant quantity amount, 50%, say, passing 10 to 20 micron range. So again, and relatively inexpensive in the scheme of things. You're looking at bulk materials that are produced in millions of tons annually. So it's a material that can be had. And I do know that the operations, or at least a couple of them, are interested in, it would be a small quantity compared to what they use for making steel. Nonetheless, another niche opportunity for using material in an application like pavement. So that's my summary of this slide. Thanks.
You go back. Okay, just go back here. Okay, yeah. So we try to measure the electric conductivity in the lab. So we look at 4 different mixed designs. One is a control specimen, is basically the binder without anything. The second second mixed design is a control specimen plus a 6% taconite concentrate. The 6% by weight, by weight. And the third mixed design is a control specimen plus the 6% GNP 4827, again by weight. And the last one is a control specimen plus 6% of a taconite plus 6% of GNP. And as a standard way to measure conductivity is use a 4-probe test. We have a current source on the 2 outer point, and we measure the voltage in the inner part. And that is on the right-hand side, you saw the specimen. So the outer 2 outlet is measuring the applied current, and the inner one, we measure the voltage. And there's a specimen dimension. Okay, so quickly, that is the result we measure. We measure conductivity. Control specimen, and you can see that for different, the scatter of the result is pretty significant, I would say, in the test. But what you can see on average, you can see that if we put the GNP and taconite all together, it leads to the most improvement in electric conductivity. Basically, if you take an average, it's almost double of what we have in the control specimen. And on the other hand, if you just put the GNP or taconite itself, it does not lead to too much increase in conductivity. So we speculate what's the reason behind this. It's not fully understood yet, but our speculation is that, for example, if we put a GNP in the specimen, in the binder, how can we make the binder to be conductive? So GNP itself, GNP itself is electroconductive, okay? Now you put those small particles and disperse it in the media of binder. So you want those particles to be very close to each other possible, so the electron can hop between them. And to do that, you want to create almost a uniform network of GNP. That is extremely difficult to achieve in experiment. Because you can think about the binder is viscous, so it's very hard to uniform disperse GNP in the binder, even though that we use a high shear mixer. We still cannot really achieve the optimum uniform network of GNP. At the same time, that you may ask whether we can add more GNP. Yes, you could, but the experiment show that if you add 10% GNP, it's very hard for you to mix them, because 10% by weight. If you look at the surface area versus gram, you see that the volume of GNP is huge because this thing is very light. So what happens is that if you add 10%, you cannot mix them. So 6% is the upper limit of what we find that we can mix with them. And even with that, it's hard to create a uniform network. And that's why that we add taconite onto it. Somehow that we find that the taconite may provide a medium that will enhance the dispersion of GNP. The mechanism of this enhancement of dispersion is still not understood well. But experiments show that if we add both together, we can effectively increase the conductivity. The next thing that I want to mention is important is the influence of humidity on this conductivity measure. And in the beginning of the experiment, we didn't think about this too much, but our lab manager did 2 tests. One is in the winter, one in the summer, and he found the conductivity is quite different. And that leads us to think about the external environment on the electric conductivity. And we show that there is a significant influence of the humidity on the conductivity measurement. For same mix, if we do the test in the winter, which is dry, we see a much lower conductivity than that measured in the summer, which is humid. And that really gives us a huge implication for damage detection. If we use this method or this material in the field, we need to make sure that we need to measure the conductivity under a nearly constant humidity. If, let's say, we do 2 tests with different humidities, the result may not be accurate enough to infer the damage extent in the material. So this is something that a special care is needed to ensure a nearly constant humidity for measuring the electrical conductivity in the field. So that is what we observe through this experimental investigation. And I will hand over to Mihai for the third part.
Thank you, Jialiang. Just want to add a couple of things that we presented the results, but actually these experiments took quite a bit of time. We had to overcome some challenges, changing the electrodes and the preparation of the sample. So, and indeed, at the end, we found out that the environmental condition limit the validity of the results. And I think this is something that our colleagues working with dielectric type measurements know very well. So, but yes, the next step, of course, okay, so there may be a chance to detect damage under ideal conditions, moisture condition, temperature conditions. The next step was, can we basically heal the microcracks that form, and in this case, do that via microwave heating. And this is a very important topic that has been discussed over the years. There was one major research project in Europe that looked at induction healing. When I say major, I'm talking about multiple universities, millions of euros funding, which obviously it's a bit different than a small project like ours. But the concept is very simple. Is it possible by applying energy by actually hitting the surface of the pavement to close these micro cracks, to heal actually the material itself. And this is what we did in this task. So next slide, please. So, and the idea was to use a microwave energy, and this was based on the information that the previous information. So we had two materials that were highly absorbent of microwave energy, and on top of that, we are very lucky to have the only company that actually has developed a microwave system that could be used in field applications. And I would like to acknowledge here the incredible work done by Vern Haag, who was one of the collaborators in this project. So obviously the choice was was using microwave. And as I mentioned, we showed before that GNP is microwave absorbent. Larry and the team at NRRI, they have been promoting this idea for more than a decade, I believe. If you look at some of the original work with Dave Hopstock, you know, that is really pioneering work in this area. So we wanted to evaluate in the lab to physically show if indeed we get healing, damage healing, when we applied microwave heating. So basically the idea is you apply heating, the viscous flow of asphalt binder you know, is enhanced, and basically the binder flows. It's a little bit more complicated, but that's the main idea. And then basically heals the micro cracks. All right, so next slide, please. And there were a number of studies in the literature that showed the potential of healing. I remember 10 years ago, Delft University, they were using steel fibers. They had a beam, they cracked it, they put it in the microwave, and then they retested it, and it showed that actually the beam could still take some loading. So it was more of an empirical type of an approach, but we wanted actually to do it following more rigorous approach based on fracture mechanics concepts. And for this purpose, we used the semicircular bend test at low temperatures. So I have to specify this was done at low temperature because there are SCB tests that were developed at intermediate and temperatures, as Wei, our colleague from Louisiana State, distinguished colleague, actually knows very well. So, but in our case, we basically perform fracture tests on a semicircular bend specimen. You can see here actually the picture, a photo of the specimen, and a diagram, a schematic of it. So you have a notch in the middle. The load is controlled in the AASHTO standard test by the crack mouth opening displacement, the so-called CMOD transducers that make sure that you actually are able to obtain the post-peak curve, very important. And we measure the load line displacement. You see there LLD transducer that allows us to measure the displacements along the force direction and obtain fracture energy. But in our case, we are interested to see what happens if we perform the test using a specimen that is not microwave, is pre-damaged and not microwave, and a specimen that is pre-damaged and then microwave. And we have here the mixtures that were considered. So while previously we showed you results for binder modified, this actually is a mixture prepared with binder that has been modified with 6% GNP and 1% concentrate. So let's look at the results then. So basically, the testing was done in two steps. So the first step was the basically the damaging of the specimen. A small damage, obviously, did not want to destroy the specimen. So we performed the test according to the AASHTO, controlled by the crack mouth opening displacement. So you see here in blue It is called the first loading. It goes post-peak, and then it reaches 80%, clearly indicated that the specimen has been damaged, is pre-cracked. And then we unloaded and stopped the test. And what we did next then, after a little bit of a conditioning time, we actually reloaded the specimen and to see what happens if you load a microwave specimen and a not microwave specimen. And the microwave was done by heating the specimen for 1.5 minutes. Basically, this was done based on some measurements that indicated that the temperature in the notch region reaches about 50 degrees Celsius, so enhancing this viscous flow. We cooled the specimens for a little bit of time, and then we retested them at -12 under control load in this case. So basically, we wanted to see what is the difference between the first loading and the second loading. So obviously, if the specimen is damaged and it stays like that, the second loading would not be able to reproduce the first loading. So we can look at the next slide then. So the peak load capacity, we looked at the peak load capacity after the second loading. These are the samples here that we tested. So you have here a specimen, a mixture sample that was microwaved and one that was not microwaved. And this is the other mixture, microwaved and non-microwaved. And you can see that from these values that without microwave heating, the peak load capacity of the specimen during the second loading, it's similar to the load level at which it was unloaded. So, which indicates no strength recovery. So it couldn't, obviously, this is where damage occurred. However, upon microwave heating, the specimen was able to regain its strength approximately 90, a little bit more of the peak load of the intact specimen. So clearly a significant difference. And I think this is more obvious in the second slide. You see here on the left-hand side, this is the without microwave heating. So the first loading is the gray one, so the blue arrow. So you see it goes to the peak and then it drops. And then when you reload it, it doesn't go above the load value where it was unloaded, as we mentioned, while the microwave heated specimen basically matches the original specimen that was tested prior to getting damaged. So this is a key indicator of healing that takes place in these specimens. And I have to mention that from what we have seen in the literature, this is the first rigorous test based on mechanics concepts that shows that actually healing occurs physically in a specimen in the lab. So, all right. So I think now Larry will discuss the various microwave systems. He's the expert. I mean, Vern is the expert, but Larry will do some presentation now. So thank you, Larry.
Okay, thanks, Mihai. Yeah, Vern is definitely the expert, and Dave is as well. The microwave systems that we're talking about here, this is just a very quick schematic of how it works, like that drawing in the center on the bottom. The target material, the asphalt in this case, a horn chamber that contains the microwave energy and sort of directs it toward that surface, a waveguide, which transmits the microwave itself from the magnetron, which generates the microwave. And we were looking at the piece of equipment on the right, lower right, is something that we did a field test on a couple of years ago at Tiller Corporation down in the Twin Cities. Vern Haig provided the equipment. I believe we were using a 50 kW generator and did some tests. So next slide, please. Yeah, the idea here, Tiller had an area where they generate a lot of aggregate. They had 3 different pavement types that we could test. One was granite, one was limestone mix, that is an asphalt mix, and another that was wasabi aggregate, or basically crushed taconite waste rock, which they put down in a separate, an adjacent portion of this area. So we were able to test all 3 doing that. So next slide, please. And the point being, and the key finding here, we heated the pavements up to about 10 minutes each, taking a surface temperature reading and then a temperature reading at 3.5 inches of depth. And you can see on the left graph, taconite being the black lines showing the steepest slope, is that that pavement heated most rapidly, and also with depth, at surface and with depth. Whereas the limestone heated a little bit better, but still took twice as long to achieve essentially the same temperatures, even a little bit more than that. And then the granite, the blue line with the dashed line heading up toward that upper left right corner, you see that crossover point. The dashed line represents measurements taken at 3.5 inches, which shows really that granite, a lot of the minerals that are contained in granite, quartz, feldspar, etc., are just not very good microwave absorbers at all. So a lot of that microwave energy was being kept continuing on with depth rather than being captured, say, in that first 3.5 inches, or from the surface down to 3.5 inches. So again, another illustration of how the material that contains microwave absorbing mineral like magnetite provides, again, another enhanced microwave energy absorbing property. For instance, perhaps taking mixed designs that incorporate the taconite as an aggregate component by itself just simply can be a much better pavement mix design for this type of application, say in the future, to provide enhanced healing, for instance, of pavements that are made of that, including whether or not you use it as an aggregate by itself or in combination with graphite nanoplatelets and concentrate in the binder. So really, this was a very good, real, full-scale field experiment that we wouldn't have been able to do without the access to that equipment. So it was very much appreciated. So thank you.
Okay, so the last part is about how we apply this material to Tack coat. Larry, want to continue?
Next slide. Oh, yeah, that's me. Sorry. Next slide, please. Yeah, the whole idea was to investigate the interfacial bond strength of the GNP-taconite-modified tack coat after subjecting it to microwave heating. And I'll just talk about what the experiments that we did to prepare those samples for that testing. Simply 2 6-inch diameter specimens were sandwiched together with a tack coat in between. And what we did here at NRI was take temperature measurements midway at the interface between the tack coat and the two lifts of asphalt, and then a lower reading of temperature after being subjected to microwave energy. Next slide, please. So again, we were provided with a normal tack coat and then the GNP-taconite-modified mixture. Both of them were subjected to microwave, while the taconite tack coat was subjected to microwave energy, and both of them. And then those specimens that were heated were then subjected to the shear strength test. You can see the photo images on the right. The microwave unit, the custom built one that was provided by Vern Haig for doing these tests. The specimens were placed underneath. That was the device was set on top and then heated for up to a period of time until both specimens reached at least 60 degrees Celsius. You can see the temperature recorded on the top and on the bottom of those specimens. So to assure that we had good heating of both, therefore And there was some enhancement of heating at that interface as well, depending on with the concentrate and GNP. So I guess the next slides will be the results of that shear strength testing. So I'll hand that back over.
Yeah, so this is a measure the shear strength use this shear device. So you will see that this. So basically, then we put the specimen in this device and then we shear it. So for most of specimen, actually failure did occur in the interface, which is the Tack code, and we measure shear strength. So the blue is the GNP, and the red is control specimen. And you see that I test at different temperatures. So we see that the microwave treated GNP-taconite mixture for Tack code leads to about 6% of improvement of the interfacial shear strength of the Tack code. Okay, so that leads to our conclusion of this project. So to summarize, basically, we try to explore the capability of damage sensing and damage healing, these two aspects of this new material GNP-taconite-modified asphalt binder and mixtures. The reason to investigate that is that in the previous research supported mean data, we already showed the different promising features of this material. So in this study, we try to further investigate what else we can do with this new material. So we find that this new material exhibits a significant improvement in conductivity, in electrical conductivity. And we believe the mechanism behind this improvement is the enhanced electron-hopping mechanism. And we also find that the humidity of the testing environment is critical, has a strong influence on the measured conductivity. So when we move to the field test, it's important to control humidity in the test environment. And based on the fact that the electrostatic field is mathematically analogous to the electrostatic field and anti-plane shear loading, we are able to derive a theoretical relationship between the conductivity and the damage extent. And we show that the GNP-taconite-modified asphalt mixtures can effectively absorb microwave energy, which provides us with effective means for damage healing. And this attractive property can also be exploited to improve the interfacial bonding for Tack code. So what's the recommendation? How we can further move to the next stage? This research basically, I will say, is a high risk, high return project. Basically, underlying ideas what we want to demonstrate that the potential benefits to use a newer technology and the materials in asphalt infrastructure. Instead of this using a more sophisticated device to measure crack, whether or not we can use the material itself to help us to detect crack. At the same time that with the new materials, we are able to using some cost-effective method, for example, microwave energy to do healing of the damage. So at the same time that some limitations are identified, it's not perfect. For example, that as we mentioned that when we use this material for sensing damage, it's important to take care of the environmental effect. As you see that most of the work are performed so far in the laboratory. So to fully investigate the potential benefits of these new technology and the materials, of course, the field experiments will be important. And we also recommend to do some limited number of proof of concept field experiments before we embark into any large-scale investigations. So, of course, this project, we are very grateful for the funding support from NLRB and MinDOT's for knowledge-based project. And we especially want to thank Glenn and Ben who really supported the idea of the critical need for innovation in new material and the pavement technologies. And in this project, we want to thank a lab manager at the U of M, Mogul, and Ron Haggs, which is our external collaborator, who provided the microwave device and the daily hub stuff. We also provide the expertise in microwave technology. And the two great students are involved in the project, and they did a lot of work in the lab, Jennifer Thomas and also undergrad student Tyler. So with that, I thank you for your attention, and we are happy to answer any questions if you have. Thank you.
Thank you, speakers. That was a great presentation, well coordinated as well. So again, just if you have any questions, feel free to raise your hand or type them in the chat, and we'll get our speakers to answer them.
If I can just add one more thing. I talked to Glenn and Ben, and they were very excited about this presentation, but apparently there is another meeting, Minroad NCAT meeting, and they would definitely watch this recording. So again, this would not have been possible without them. And as my colleague mentioned, Professor Le, I think the big challenge is to do a field validation, a limited field validation of this technology. There is a lot of interest in the application of a graphite nanoplatelet. Other people don't have a taconite like we do have, Larry. So, but I know of two products, asphalt products that have limited amounts of graphene or graphite. One is it's a mixture developed by a company in Italy that was placed recently on a portion of an interstate in Italy, and also some limited application with recycled asphalt that was recently performed in Northeast England in Northumberland region, so with University of Manchester there. So there is interest, but I guess the biggest challenge is to actually have a field study to validate this technology. Again, thank you for the opportunity to present our work.
So I don't see any questions yet, but I will ask one of my own, and this would probably be for Jieliang. I know you talked about the difficulties of mixing in the GNP, and that 6% is really the max, and that you found that adding taconite helped the mixture, getting it mixed more uniformly. Did you try adding more than 6% taconite? Would that allow you potentially to get more than 6% of the GNP distributed?
Good question. I don't think we tried anything more than 6% of taconite. We haven't tried that.
And then one more question, which may be for Mihai, but I noticed on the testing you did for the microwave healing, you used, is it correct, you used a 1% taconite mixture for that test?
Yes.
That is correct. Yes, we use
Yes.
6% and with 1% concentrate. Yes.
Would you be thinking at all about doing the same test with a higher taconite percentage?
Yes, there is one aspect that we have not discussed because taconite concentrate it's a very fine aggregate that could be interpreted also as filler, which then changes a little bit the properties of the mixture. So there are some limitation on how much filler you can add. The binder content then needs to be changed. So we try to limit the use of taconite concentrate from that point of view. But that's an interesting idea. So maybe we should try and do that. But it is possible if we add more, maybe the mix will become maybe more brittle at low temperatures, but it's just speculation. But that's we looked at the filler content in typical mixtures, so that's why we sort of limited the percent of concentrate used.
Thank you. So we do have a question from Rich. We will let him answer. Well, I'll read the question and then we'll let you guys answer. How does microwave compare with infrared for inducing a self-healing heat into asphalt? Is there even a comparison?
I guess I could take that one. Yeah, we looked at, we did a project a few years back, supported by MnDOT, and where we looked at infrared and microwave heating to do pothole repair, for instance, and modeling that was also done by Dave Hopstock during that project. Infrared, they're totally different. I'll just answer that very quickly. Infrared heating really is a top-down heating mechanism. So you get very high temperatures, for instance, near the surface, but very quick drop-off in temperature with depth. Microwave heating is more uniform and provides heating with depth. In fact, a little bit higher, perhaps, say a ½ inch to 1.5 inches down in the pavement, even than at the surface. Yet the surface is still getting warmed up. So there are two different mechanisms. Infrared has limitations simply because of that. Again, heating very, very rapidly, say at the surface, but a quick drop off in temperature with depth. I think microwave is a better technology for the application that we're talking about today.
If I can add something, there are some infrared technologies that have been used, I believe, in Ohio with a new pothole material. The issue is with infrared, as Larry mentioned, it's at the surface, and it can actually increase temperature in certain areas and basically age the binder, the asphalt binder, if not even basically burn it, so to speak. While microwave is basically heating the aggregates, the filler, the aggregates, the graphite nanoplatelets, and this does not create this potential for aging of asphalt material, which is obviously very important because an aged asphalt binder is brittle, becomes brittle and cracks. So for what it's worth. Yeah.
Thank you, Rich, for that question and for your responses. It looks like we have a hand raised from David, which we're going to unmute you, David, so you can ask your question.
I think, David, you can now go ahead and unmute yourself to ask your question verbally.
Can you hear me now?
There we go.
Okay. Well, first of all, I want to congratulate you on a very clear presentation. My question is, I think Mihai referred to what the next stage would be. So I wonder if you could elaborate further on what your ideas were for what the next stage in the research would be.
Thank you, Dave. That is a very good question. We have many ideas, but we cannot obviously pursue them by ourselves. So basically, one challenge is to mix the materials on a scale that is applicable to a small field application. And this has to be done with a partner from the industry. And then, of course, we need another partner from industry to place this material down and then monitor the performance. We had a number of ideas on how to mix it efficiently. I mean, theoretical ideas. We were not able to find an industry partner that was interested to pursue this, which I think it's understandable, because it's additional cost, maybe some changes in technology, but we hope that this would become possible in the near future. So at least we would know if it works so well in the lab. If this would work well in the field as well, it could be great because it's not just the sensing part, but as my colleague Professor Le showed at the beginning, we've seen a very significant improvements in actually cracking resistance, and not just the asphalt binder, but we also have data on asphalt mixtures in which we show the fracture energy actually can increase by 50%. And then also the other capability of reducing compaction effort. But again, this has to be tested in the field. This has been a big challenge. We have been working on this for 2-3 years now. And I have to admit that we are not successful at this point, but we still hope this would be possible in the near future. So I hope this addressed your question, Dave.
Yes, thanks.
I was curious, once you add kind of the powder mixture to the material, do you need to place it in a certain time frame to be effective, or is it something you'd be able to mix at the plant so you'd have like a whole batch that agency could use, for the whole day?
There are no limitations. The important thing is to be able to mix it thoroughly, and it can be done in a hot mix plant, probably as you mentioned, in a batch plant. Probably it would work better to create a small batch and add it during the mixing process at the very end as a dust type material. But this poses some challenges. At some point, we are also thinking of adding it directly in the field, but that could be a bit more challenging, using the hopper of the paver. So there are many ideas. You could also mix it in the binder, but and then the binder obviously can be added to the mix, but this also has its own challenges. So yeah, so but there are no limitations. Once you mixed it, there are no limitations in terms of when you can do it. So.
We can field a couple other questions if anyone has any, want to raise their hand or type it in the chat.
I maybe have one more. So towards the end of the presentation, you talked about using it as a tack. Did you compare it to the conventional tack material that is kind of industry standard now?
I can address that, or Jialiang, if you want to discuss it.
No, you can do it.
So this is a comparison of the regular tack coat and the one that has the GNP-taconite material. And after microwaving, and you can see, so basically we perform this interface strength testing. It was more a proof of concept, because this strength test, interface test, bond strength test, actually there are many variations of that. And my colleague from Louisiana State, Louis Muhammad, he did a lot of work on tack coat, very nice work, but we are just trying to show differences. And it appears from this limited testing that there is some minimal enhancement of the strength, of the bond strength between the asphalt layers, which maybe in the field could be significant in increasing performance, limiting the lamination and longitudinal cracks and so on. So it appears to be, we see some improvement compared to the regular tack coat. But this was very limited, more proof of concept, as I mentioned. So.
Okay.
Any other questions that anybody has? All right, well, thank you very much. I'm going to turn it over to Christy.
Thanks, Beth, and thanks so much for the presentation. We're going to transition into the round robin section of our meeting. So we're really looking to hear from the participants on just any ideas you guys might have on future topics you'd like us to have as presentations at these meetings. We do have meetings, typically one in the spring timeframe and one in the fall. we're also interested in just hearing any transportation infrastructure issues that your organization is focused or facing, just to help us with ideas for future research projects, or really if there's just any information or updates that you have that you want to share with the group today. So you can raise your hand and we'll unmute you. Otherwise, if you want to just put any information in the chat and then I can read it out loud for the group. I know at Hennepin, we have a lot of old pavements, so we're always looking for new innovation and ideas to preserve the system because there's not enough money to reconstruct it. So a lot of those pavements are gonna probably be, you know, approaching 80 plus years old before we have funding to reconstruct them. So do we have a quiet group here today?
I guess I'll just speak up quickly here. We do have another project, a current one, LRB, MnDOT, collaborating with Mihai and Manic Barman on friction aggregate that is high friction surface treatment. And we have a couple of few test sections located near NRI here. Tomorrow we'll be going out with a dynamic friction tester, British Pendulum. We've been, those test sections were installed in July, at the end of July, and this is an ongoing project that will continue through basically through July of 2024. Lock wheel skid testing has been performed to give us some baseline data, and that work will continue on a semi-annual basis in the fall before snow plowing and in the springtime after snow plowing, so we can get an idea of how those pavements, how those surface treatments are holding up, and do a comparison between taconite based and then calcined bauxite, which is sort of the gold standard for high friction surface treatments. So this is a real field application on a decent size scale on a low volume road here in St. Louis County. I just wanted to give people an idea. That's a current project that we're working on right now.
Thanks, Larry. Well, not seeing any other comments.
This is Katie. I can just
go ahead.
jump in here. Katie from CTS, Center for Transportation Studies. Just another plug for the CTS Research Conference coming up on November 4th. So if folks are interested in previewing the program, that's posted online, and we welcome folks to register. Thank you.
Yeah, also just another reminder, we do have those fall webinars coming up on October 26th, and then on November 9th. So I think Katie provided links if you're interested in signing up for any of those. So I would like to just, thanks to our speakers again. It was a great presentation, and thanks for all the participants out there, and have a great day.
Thank you very much. Thanks, everybody.
Thank you.
Thank you. Thank you.
Bye.
Bye.
Bye.